Salut tout le monde. Welcome back to another differential geometry reading stream where I, Anthony, read from Differential Geometry by Erwin Kreisig. But about that, so currently we're in chapter 7 and we're at section 74, which I'll have you know is the shortest section. It's not even a full page because we get to section 75 at the bottom of the page, and I almost read that section in the last video. I will say you may notice that the video quality is a little bit different in this video. That's because I got an actual proper streaming webcam. I had a different one, and like the FaceTime camera isn't really that good. None of the built-in webcams on any laptop are ever any good for serious, streaming. I had this other external webcam and it was really awful. The video was kind of decent. No, it wasn't. It was really bad, but it would keep on cutting out. Like something was up with the cable. So I was like, you know what? I do rewatch these videos, and I don't just rewatch the differential geometry videos. I watch my old videos too, if I'm being honest. And so, yeah, I figured that if I'm going to be watching this video again in 5 years, might as well get the nice streaming webcam. Anyways, I was going to read section 74 last video, but then I realized as I was reading like supplementary other sources about the Bianchi identities, really for a while now, we've been in not necessarily differential geometry, but really Riemannian geometry. You could say probably starting around the geodesics chapter, or maybe even earlier, like when I was talking about length, angles, and areas on surfaces. That was just kind of like a reduced down take on the same thing with Riemannian manifolds. So anyway, these could more properly be called perhaps Riemannian geometry streams at this point, right? But anyways, I was also thinking like these videos, frankly, take a long time for me to put out, mostly because of the time it takes to edit these videos, okay? So in all my other episodes previous to this one, I would have this camera right here, which is like a point and shoot camera, right? And I would also be recording the audio externally. I would have that on voice memos. And then I would also be recording the screen recording with like the book or whatever on screen, or like PowerPoint slides, right? And then I would, after the fact, edit those together in Final Cut Pro. And so like I would, edit these like intros and stuff like that, and I would clean up the reading takes so that it doesn't sound just atrocious to the ears. But I realized that the video and audio tracks are like 1,000th of a percent different in the rates that they record. Not only that, but I think Final Cut Pro, like when I don't know if any of you are familiar, probably not with editing, but you have the audio and video tracks and you can like blade cut them, almost like if you had physical tape, and you could literally cut and paste your film reel together and have your edited production or whatever. But now you do it all digitally, right? But the tools are the same. But anyways, the increment that you could blade the audio and video wouldn't necessarily align. And that, on top of the difference in the rates being off ever just so slightly, after about like 15 minutes of recording, they would be out of sync by a couple seconds, the audio and video, which was kind of annoying. So I was like, you know what? I'm just going to get used to using OBS, and I'm going to do it the way 99% of other people who are like streaming do it, and just have the webcam, audio, screen recording all going into one file all at once. Anyways, so I was doing the whole Bianchi Identities preparation, right? End of last episode, we were looking at the Ricci identity. Now we're at the Bianchi identities. Turns out those are both related as far as understanding curvature from like a Riemannian geometry perspective. And so like I realized that in my preparation for this episode, right? And then I was thinking, it's been basically like a year since I started the differential geometry reading stream episodes, and I took all of my notes from all of the last like 31 episodes, including I like typed out my intros for some of them, and I made this binder here with all of those notes. Okay, that's 198 pages. How do I know? Because I bought 200 sheet protectors and I had 2 left over. And I was like, it's been about a year. I've got this full binder of differential geometry notes. Maybe these are going to start to be Riemannian geometry streams. Anyways, so I'm going to take another step back here. So obviously started off reading Differential Geometry by Erwin Kreisig, and we're getting towards the end, right? And even in the preface to this book, it says, right, the presentation in this book may also be considered as a preparation for the Riemannian geometry of n dimensions. And I had talked in previous videos about how one of the shortcomings of this book was that we limited in the treatment our number of dimensions to n equals 3, supposedly to fit more realistic space dimensions. Kind of weird considering that space-time is really the fundamental way of thinking about things, and that's 4 dimensions. But I kept on thinking about that of like, this book kind of fell short on the whole Riemannian manifold aspect of things. So I was like, how could I take things to that level, right? And so I had found this, it's not really Stack Overflow, like if you're programming and coding and you've got something and you upload it to Stack Overflow. It's not Quora, but it's another one of those like question forum websites, Math Overflow, right? And I cut out the person's question, but they're basically asking for a differential geometry book that's beyond Intro to Smooth Manifolds, which I've talked about again in another video, or also beyond Riemannian Geometry by De Carmo, which is a book that's on my list to get a physical copy of. But basically this person was looking for books that are more advanced than that. And towards the bottom here, we have this suggestion of a book called Riemannian Geometry by Peter Peterson. It says this book is very definitely advanced. You need to read at least 3 other differential geometry books before this one. So, I definitely picked up a copy of that one. And then we have another suggestion here, which is above it, for Lectures on Differential Geometry by Schoen and Yao. And this one says this is about as advanced as it gets. You need to read at least 5 other differential geometry books before starting this one. So I don't have a physical copy of that one yet, because I haven't even really properly read Riemannian Geometry by Peter Peterson. But it's like, okay, where are you going with this, Anthony? Why are you just buying all these books? I was like, okay, let's just say we count Differential Geometry by Erwin Kreisig. That's number 1. And then another book that's at the same level, we could say, that I've talked about in previous episodes is the Kuhnel book, which was suggested, or it's like the required reading for the MIT OpenCourseWare undergraduate differential geometry course. And it's about at the same level as Kreisig differential geometry. And I'm actually going to look at the table of contents for that one in a sec. I haven't read every single page, obviously, of the Kuhnel book, but I've skimmed the parts that aren't exactly in the Kreisig differential book, okay? Let's say that's 2 books right there. Then we go with Intro to Smooth Manifolds. That's like number 3, let's say, because this goes over, as I'll point out here in a sec, this is just like pure differential geometry, different than Riemannian geometry, okay? That's like 3, but then we'll play it safe and we'll have this other one right here, which I've seen syllabi online. This is like differential geometry 2 sometimes. People will use this. This was also formerly in like the 80s or 90s published with a different name. It was like Intro to Riemannian Curvature, something like that. This is just like the new edition published in the early 2000s. So it's like, okay, that's 3/4 books maybe. Then Peter Peterson, Riemannian Geometry. And then frankly, from what I've read here about these other books, I would maybe also go into Comparison Theorems in Riemannian Geometry by Cheeger and Eben, probably butchering the names. And then also down towards the bottom beneath Peter Peterson, Fundamentals of Differential Geometry, Serge Lang, and then Lectures on Differential Geometry, Schoen and Yao. Where am I going with this? Well, all right, so this is the table of contents for differential geometry by Erwin Kreisig that I've been reading so far. Chapter 2, Chapter 3, and Chapter 4, I would say, plus Chapter 8 parts of, are like theory of curves, theory of surfaces, differential geometry proper, 1 semester of differential geometry. So, okay, yeah, preliminaries chapter 1, but mainly chapter 2, chapter 3, chapter 4, and chapter 8 here. But then chapter 5, geodesic curvature and geodesics, chapter 6, mappings, chapter 7, which we're in now, absolute differentiation and parallel displacement, and other parts of special surfaces in chapter 8. That's all Riemannian geometry, really, as I'm finding out. How do I know? All right, so this is what I'm saying. We've got the table of contents for the Kuhnel book. Curves, surfaces, manifolds. I'm not going to put it on screen right now, but in the intro to this book, it spells it out. Chapter 1, notation and preliminaries, prerequisites, whatever. But then, okay, chapter 2, curves. Chapter 3, surfaces. 4, intrinsic geometry. What's in that? Okay, covariant derivative, parallel displacement, theorema egregium, Gauss-Bonnet theorem, Gaussian curvature. Okay, so anyways, the point I'm trying to make here is that the next 4 chapters here, Riemannian manifolds, curvature tensor, spaces of constant curvature, Einstein spaces, that is all technically Riemannian geometry, I guess, right? And it's kind of like made more clear, explicit in the Kuhnel book. Maybe that's probably because the Kuhnel book is a more modern book, right? Because Differential Geometry by Erwin Kreisig was penned down, written in the 50s. I think the first edition was like 1959. So it's like, sure, it got translated into English and reprinted by Dover in like the 90s or the early 2000s. But nonetheless, in this Peterson Riemannian geometry book, or maybe it was this Intro to Riemannian Manifolds book, one of the intros of these, it says, anything that is proven after 1950 in this subject is modern. Anything before that is classical. So, okay, and going back to this Kuhnel table of contents, chapter 8 has stuff about like the Weil tensor and stuff like that, which is not even gone over in the Kreisig book. But being that I started doing this so that I could learn the math hardcore for general relativity, it's like I'm not going to skip that stuff, you know what I mean? Yeah, and I was going to say what I really appreciate is that this Intro to Riemannian Manifolds book, sure, it's like technically maybe you could say a differential geometry 2 book, and I haven't even gone all the way through Intro to Smooth Manifolds yet. So why even start reading this book yet? Well, chapter 1 has this great, maybe like, I don't want to say holistic, or just like it's an intuitive look at curvature. It's not technically rigorous right off the bat per se, but like I said, it's trying to build that intuition for what exactly is curvature. Emphasizes here, the purpose of this book is to introduce the theory of Riemannian manifolds. These are smooth manifolds equipped with Riemannian metrics. Again, smooth manifolds, that's like the whole point of, obviously, John Lee Intro to Smooth Manifolds. Whoops, going on here. Which allow one to measure geometric quantities such as distances and angles. Going back to my most popular differential geometry reading stream episode so far, you know what I mean? Goes further on down here, the central unifying theme in current Riemannian geometry research is the notion of curvature and its relation to topology. So I think going forward that is helpful to keep in mind. Yeah, and then, okay. So let's just get it out of the way. This is the shortest section in the book. I was able to fit it all on one PowerPoint slide. And so, yeah, let's just read it. I'm like 20 minutes into this already, so let's just read what we came here for. Section 74, Bianchi Identities. We shall now prove the following. Theorem 74.1. The covariant derivatives of the curvature tensors given in the previous section 46. So there were two curvature tensors given. Satisfy the following identities of Bianchi. And we denote those curvature tensors capital R. So we have R superscript sigma and then subscript alpha nu beta comma tau plus R superscript sigma subscript alpha tau nu comma beta plus capital R superscript sigma subscript alpha beta tau comma nu is equal to 0. And the second identity of Bianchi is where we have R sub sigma alpha nu beta comma tau plus R sub sigma alpha tau nu comma beta plus R sub sigma alpha beta tau comma nu equals 0. So in the first and second identities of Bianchi, those nu indices or tau indices kind of rotate around there. But as we'll see here in a little bit when I go to look at Gravitation by Misner, Thorne, and Wheeler, which has a whole entire chapter of 15 pages just on the Bianchi identities, we're going to see that this whole equals 0 of the Bianchi identities turns out to be an expression of conservation. So anyways, now for the proof. In the case of two-dimensional Riemannian spaces, that is surfaces, this theorem is a trivial consequence of previously given 46.9. What is that? Okay, which is just a statement that the covariant curvature tensor is skew symmetric with respect to its last two indices. So we will now prove the theorem for general values of n greater than or equal to 3. In the previous section 47, we showed that on every surface there exist coordinate systems of such a type that the Christoffel symbols vanish at an arbitrary fixed point capital P naught. It follows from the proof that the same fact also holds in n-dimensional Riemannian spaces when n is greater than 2. With respect to such a coordinate system, the representation in section 46 of the mixed curvature tensor at that point capital P naught reduces to curvature tensor R superscript sigma and then subscript alpha nu beta is equal to partial Christoffel symbol sub alpha beta superscript sigma partial u nu minus partial Christoffel symbol sub alpha nu superscript sigma partial u beta. And I'll also say that I read that out as Christoffel symbol because Obviously, there are partial derivatives here. There are going to be subsequently partial differential equations associated with these things, which get broken into differential equations in order to solve them and all that. You probably know this, but when you then dig into those PDEs, sometimes you have solutions involving gamma functions. And I just read Christoffel symbol so that mentally I'm not like bringing to mind gamma functions when I read that anyways. But that's just me. Furthermore, at capital P naught, the covariant derivative reduces to the ordinary one. Indeed, since the Christoffel symbols vanish at the point capital P naught, by differentiating the relation from section 46, we obtain capital R superscript sigma sub alpha nu beta comma tau is equal to partial R superscript sigma sub alpha nu beta partial u tau is equal to partial squared Christoffel sub alpha beta superscript sigma partial u nu partial u tau minus partial squared Christoffel sub alpha nu superscript sigma partial u beta partial u tau. From this, it follows that the first Bianchi identity holds at the point capital P naught, and with respect to the above special coordinate system, since the left-hand side of the first Bianchi identity is a sum of components of tensors, and therefore a component of a tensor, it is 0 at capital P naught in every coordinate system. Since our point capital P naught was arbitrarily chosen, the first Bianchi identity holds at any point of the space under consideration. We will now prove the second identity of Bianchi. Theorem 72.1, which in the previous section 72, of course, states the covariant derivatives of the tensors g sub alpha beta, g superscript alpha beta, and Kronecker delta sub alpha superscript beta are 0 tensors. This is valid not only for surfaces but also for Riemannian spaces of higher dimension, as can be immediately seen from the proof. Hence, by this relation from section 46, where we can lower the, maybe I'll just have it on the screen, maybe not. But anyways, by this relation from the previous section 46, we have that our curvature tensor R superscript sigma sub alpha nu beta comma tau is equal to, we have this quantity here, G superscript sigma lambda, then times R sub lambda alpha nu beta, closed quantity, all then having a subscript of comma tau. This is equal to G superscript sigma lambda, then times R sub lambda alpha nu beta comma tau. And using this relation, we obtain the second identity of Bianchi from the first one. So there you have that, but so there you have that, and I'm not going to read this, but now from some notes that Peter Peterson, the author of Riemannian geometry, which I showed you guys earlier, you could do a different proof of the Bianchi identity here, and I'm not going to read this one out loud, but you can just see that there are levels to this game, right? I could read out all of the notation here, but it's like, have we gone over what a Lie derivative is yet? No. We're just bringing to bear more powerful tools, but this Bianchi identity still holds, right? That's why when I came across this in the Kreisig book, I was like, okay, this might be an inflection point in this series where the episodes, there's definitely more to be done with this series. Let me just put it that way. Because, here we have then, continuing the proof to get the second Bianchi identity. But I was like, okay, what is this all about? We're trying to relate this back to general relativity. And like I said, the Nisner-Thorne-Wheeler gravitation book has a whole entire chapter dedicated to the Bianchi identities. And kind of true to form to physicists, we don't really derive from the ground up the math. But in the first paragraph here, we kind of just get indoctrinated in with a mantra here, which is the principle that the boundary of a boundary is 0. So everything I just read, including the shortest section in the entire Kreisig differential geometry book, doing the proof of the Bianchi identities, I'm probably not going to remember that if you ask me that in 6 months. But I will remember that the boundary of a boundary is zero. And, we do all this stuff looking at thinking about the boundary of a three-dimensional box and how, there are anti-directional vectors at the corners, the edges of this box and stuff, which cancel out. That's how you get the boundary of boundary is zero. And then, generalizes to if you have a hypercube and all this stuff. But I'm not going to go over that now. I will note, however, I've been reading gravitation, and the notation is atrocious, which I have. Yeah, the math notation can be a bit atrocious here. We have these like stars and mix of bold and not bold, and the symbols aren't very aesthetic. But I think those weird stars are hard to read because maybe from far away it almost looks like a dot. So I just don't like it. But, this book is like published for the first time in the 70s, and now everyone just uses LaTeX. But boundary of a boundary is zero is very helpful. This also is something you would not see in a math book where you have arrows pointing between the different derivatives and stuff like this, right? But it does help and go a long ways to helping to understand conceptually, intuitively what's going on. And having right here the contrast of in electrodynamics with Maxwell's equations, you have a conservation statement, and the goal of the Bianchi identities is to have the same kind of thing going on in geometrodynamics. So it's a bit loosey-goosey on the math, and the notation isn't as pretty. It's not as modern and all that stuff. But, you learn a lot. And finally here, I had to put this in there because I mentioned this 2 videos ago now. This is from the recommended reading section for a graduate level general relativity class from MIT OpenCourseWare. And I mentioned in a previous episode where this recommended reading list is like a who's who of general relativity books. And the entry here for Wald's general relativity book says that it's, this is like the mathematical hardcore one of the bunch, but says a few pedagogical gems are hidden here. For example, the nicest proof of the Bianchi identity that the professor of this course has ever seen, or the instructor of this course, whatever. Anyways, but we have that exact proof right here. So I'm not going to read it, but part of it is that, if we go to the last statement, 3.2.24, we have omega sub e times nabla with a subscript of subscript a and then capital R, not subscript. But then we go back to subscript BC, close the square bracket, subscript D superscript E equals 0. I don't know, that was a little bit sketch. So yeah, I'm gonna flex right now, and I'm just gonna gotta fix this. Boom, flexing for you guys. Also, I'm still keeping open the giveaway for the Figure 69 cone shirts. The Discord, Patreon, and all that is still coming. And I am sorry about saying that I'm going to do these weekly still. It's been a rough start to the year so far. But as you can see, I made my setup a little nicer, so it takes way less time to edit these. And I don't know if you noticed or could tell from this, but I've kind of planned out, put more thought into where these episodes are going to go in the future. So when I finish reading Differential Geometry by Erwin Kreisig out loud, there's more to read, and we're still learning about general relativity. So yeah, sign up for the giveaway. The link is in the description. I don't know. 35 minutes, perfect. Peace. See you guys in the next one.